Now that we have the understanding of how winds can induce Ekman pumping and Ekman suction, we can go back to the large scale picture, and that's being shown here. We have the easterlies and the westerlies. As I said, you can curl your fingers around them, and that gives you the sense of the vertical velocity that would be induced by these winds. For the subtropical gyre, we get a thumb pointing into the ocean in the negative z direction, which means it's negative vertical velocities or Ekman pumping. Right? So you have Ekman transport converging into the middle of the subtropical gyre. There is a little asymmetry there again, to remember that the F is higher in the westerly latitudes and lower at the easterly latitudes. So you can also think of flow being deflected to the north here, less than it is being deflected to the south here. Nonetheless, there is a convergence into the middle of the gyre, and there is a Ekman pumping. Okay, so this can be seen in terms of the dynamic height or sea level, which we already saw. We haven't defined dynamic height yet, but this is somewhat like the geopotential height. We will see, we'll define what it is. Actually, we already did that in the last chapter. The integral of, was it rho dz or some such thing, right? You look it up, and that's the dynamic height. Okay, we remember we did the dynamic method of calculating geostrophic currents at depth, right? Or even at the surface. In the bowing down of the isopycnal, so this is looking at depth in meters of the sigma 26.5 kilogram per meter cube. We had seen this before in the 9th chapter, where we said this is in the middle of the thermocline, and it gives us the sense of the doming, and so the lifting of the isopycnals in the upwelling regions and the bowing down of the isopycnals in the subtropical gyres. Obviously, this corresponds well with the dynamic height or the sea level. Why? Remember always the same simple rule, that when the isopycnals bow down, the sea level goes up, and when the sea level goes down, isopycnals are domed up. Okay, so here you had upwelling, so thermocline being domed up, so sea level going down. And we had already mentioned that the sea level rise from the east to the west here is about 50 centimeters. From the equator to the middle of the gyre is about 2 meters. So ships are going uphill in these directions. Okay, so the non-divergence of the geostrophic currents tells us for incompressible flow that du dx plus dv dy plus dw dz is 0, whereas the ageostrophic component can be written as divergence of UAG, horizontal divergence of the ageostrophic component, plus dWdz equal to 0. So we have split the total velocities into geostrophic and ageostrophic components. Why? Obviously, we're going to make this into the Ekman pumping or Ekman suction, right? So that's where we are headed with that. So W equal to 0 at the surface, because the air is not water is not going out of the ocean or coming into the ocean, except there is precipitation and evaporation, which are very small compared to the actual Ekman pumping and Ekman suction, as we will see. Okay, the numbers here tend to be order 30 meters per year, whereas the precipitation evaporation tends to be in the order of 1 meter per year. Okay, so we can make this assumption at the surface. Our Ekman transport again is tau wind crossed with the z hat over F. Remember, the atmosphere, we were always going to Z hat P to avoid density. Here, density is not been a problem so far because we are still going along with the incompressible rho ref, but of course we have sigma. So rho is written as rho ref plus sigma, so the sigma equals 26.5 basically means the density is 1026.5 kilogram per meter cube. Okay, so W Ekman is 1 over rho ref, divergence, horizontal divergence of M Ekman. That's du ageostrophic dx plus dv ageostrophic dy. But M Ekman we had written in terms of the wind stress divided by F. So in that case, Ekman pumping just or suction just becomes 1 over rho F Z hat dot the curl of tau wind over F. Okay, very simple manipulation. We took the equations and replaced these terms with the Ekman transport term. That's all we did here. So that allows us to write Ekman pumping in terms of 1 over rho ref d dx of tau wind y over F minus d dy of tau wind x over F. All these equations have similarities to each other with just a slight difference, so you can follow the logic very easily. Okay, this is new in the sense we are introducing frictional forcing with the curl so that water is converging or diverging, and there is a dependence on F, of course, because the convergence and divergence is going to be affected by the rotation, as I said, because the trade winds push the water to the north less than the westerlies pushing the water to the south, because F increases with latitude. Okay, so tau wind y is varying in the y direction, and tau wind x is varying in the x direction, so F will be varying differently for x versus y, and we have already said many times that in general meridional winds are much weaker than zonal winds. Not always true, but in general. So Ekman pumping in this case turns out to be the rho ref, which is 10 to the 3, pure water, typical wind stress magnitude of 0.2 Newton per meter squared. Be familiar with the units. And F, order 10 to the minus 4 in the mid latitudes, times the scale of the flow, which is 2000 kilometers. Okay, that gives us a typical Ekman pumping velocity or Ekman suction velocity of 32 meters per year. 32 meters per year. Okay, so we are saying things that are kind of maybe confusing at this point, but we'll see how this happens. We are talking about horizontal motion creating vertical motion, convergence and divergence. Horizontal motions, we have already said, are in the order of centimeters per second, but vertical velocities are 32 meter per year. That is really, really small. How does that happen? We will see that. So anyway, we can use that formula from the previous page and just compute Ekman pumping, Ekman vertical velocity using the winds and the wind stress curl. Obviously, you will see that there is pumping in the subtropical gyre and there is suction in the subpolar gyres. Since there is a denominator has F in it and F goes to 0, we cut off the calculation of Ekman pumping at some low latitude. So you don't have Ekman pumping definable with this formulation on the equator. You have to reconciliate this with the fact that we were blowing trade winds, we were diverging water away from the equator and creating upwelling anyways, right? So there is dynamics that can still allow you to have Ekman divergence and vertical motion of water, but not in the sense of Ekman velocity and the wind stress curl. that is dependent on F. Okay, that's the story. So this I showed before. The theory that is derived by Hyde and Titman in 1967 shows W Ekman to be omega over 2 times nu over 2 omega plus omega to the 1/2, where nu is 10 to the 6 meter squared per second, the kinematic viscosity of water. And the lab experiment that we saw, omega was set to 1 radian per second, the rotation rate of the tank. Very slow, 1 radian per second, 10 RPM. So omega is 0.5 radian per second. That was the rotation of the disk that was giving the cyclonic or anticyclonic circulation. And Ekman pumping there was 1.5 times 10 to the minus 4 meter per second. So in figure 10.9 from the lab experiment, fluid is being sucked up at a rate of 9 centimeters every 10 minutes. So depending on the height of the water tank, you are basically circulating water at those vertical speeds. Again, horizontal speeds will be much larger. As we will see, there is an amplification factor that converts the slow vertical velocities into much faster horizontal velocities. Okay, so here is comparison of the evaporation and precipitation and E minus P, which are in the order of 1 meter per year. Okay, so contour intervals here are 0.5 meter per year. So obviously Ekman velocities in the ocean are much larger than the exchanges of evaporation and precipitation at the surface. Okay, that's why we assume that the W is 0 at the surface when we integrated for Ekman pumping. Okay, simple concepts, but make sure you understand, because obviously we'll keep adding complications as we go along.